Hi everyone, welcome to Rate of Change Day 2. I want to start off actually with some bell work, and our bell work is simply to evaluate this limit. Minus 16 over x minus 4. Okay, so how do we do it? Well, remember, I always recommend trying direct substitution first. If I plug a 4 in, I'm going to have 4 minus 8, which is negative 4 squared minus 16 over x minus 4. So I'm plugging in a 4. I get a 0 on top. I get a 0 on the bottom. That means I'm not done. I need to try some algebraic manipulation. All right, so let's do some algebraic manipulation. We're going to FOIL up here and have x squared minus 16x plus 64 minus 16 over x minus 4. And if we combine like terms in the numerator, we'll have x squared minus 16x plus 48 over x minus 4. So does this factor? I hope so. Let's try. Limit as x approaches 4, x minus 12, x minus 4 over x minus 4. We can cancel out these common factors, and this was what was keeping us in 0 over 0 land. Now we can do direct substitution, 4 minus 12, and get negative 8. Okay? Don't forget to evaluate limits. All right, so now today's main topic is dealing with questions that involve rates of change, growth, decay, increasing at an increasing rate, maybe, velocity, acceleration. Let's take a look at the first one. I looked up some data about farmed salmon, and the numbers for farmed salmon look like this. In 1988, we were farming on the planet approximately 1 million tons. In fact, I think what I'm going to do is say millions of tons. 1 million tons. That's a lot. That's a million times 2,000 pounds. Okay, then in 1995, we were up to 2 million tons of farmed salmon. And then in 2004, we were up to 3 million tons. So I'm going to call this t equals 0. And this, therefore, is t equals 16. And I like to think that even though we could grow a lot of farmed salmon, the amount of farmed salmon that we could possibly grow is not infinite, and that there is an upper carrying capacity to this option. So I went with a logistic model, and I did a logistic regression for this, and I came up with this. Farmed salmon is a function of time, 3.4586 over 1 plus 2.458 6344 33 to the negative 0.173 607 5728 t. So it looks like the upper boundary appears to be about 3.5 million tons. Okay, so let's take a look. I'd like to know the following. What's S prime of 31? What's S of 31? And what do each of these mean? Well, let's start with S of 31. And yes, this is a calculator question. So here's my calculator. And I've conveniently typed in our salmon farming function here. But I'm going to go over and use the table. And I'm going to type in 31. And I get S of 31 equals 3.4199, or approximately 3.420. Now, what are the units here? Well, we know the units on S of t are millions of tons. So in 2019, we should have farmed 3.42 million tons of salmon. Kind of want to go check on the internet. But what about S prime of 31? Well, I'm going to use my calculator to figure that out. I'm going to come down here to y2, and I'm going to do n deriv of y1 in terms of x for all x values. Okay? You could certainly do this on the main screen. I'm going to go over now to my table. And now my table will give me not only function values, but derivative values. So for 31, we've got 0.0066. And what are the units on this? Well, this is the rate of change, or slope, of S of t. And what S of t has is millions of tons on top and years on the bottom. So what do we see from this? We see we're going to have millions of tons per year. And we notice that this number is positive. So we know the amount of salmon being farmed is increasing by 0.007 million tons of salmon per year. That's how I understand that. It's not growing much, but it's still growing. Do we expect that? Well, think about it. I went with a logistic model. A logistic model is always increasing. But once we get past the inflection point at L over 2, we're increasing more and more slowly. The slopes here are not as steep as the slope here. So the rate of change is decreasing. That means the second derivative. Well, let's take a look at the second derivative. S double prime of 31. So to figure that out, we're going to come over here and we're going to go to y3 and we're going to do n deriv again. But this time we want the derivative of y2, not y1. With respect to x, with respect to x. Go back over to our table and scroll over. There we go. And so I see that y double prime of 31 is negative 0.0011. So what's that mean? Well, that's a rate of change in S prime with respect to time. So it's millions of tons per year. The amount that we're increasing by, because we know we're increasing because S prime is positive, that amount that we're increasing by right now in 2019 is decreasing by 0.0011 million tons per year every year. So remember how this slope wasn't as steep as this one? Well, at time equal to 2019, that change from one to the next was negative 0.0011 millions of tons per year per year. So this number is going to keep getting smaller by this amount each year at this moment. But as we go further, this number will change, and therefore this number will also change. Okay, so that's first question. Oh, and is the amount being farmed increasing or decreasing? The amount being farmed is increasing because our derivative is positive. If our derivative was negative, the amount being farmed would be decreasing. What we can say is, because the second derivative is negative, is that even though the amount being farmed is increasing, the amount being farmed is increasing at a decreasing rate. Amount farmed is increasing because S prime is greater than 0, but at a decreasing rate because S double prime is less than 0. Okay, there's our first question. Second question. Second question, we've got S of t equals cosine of t. Now remember when we were drawing the graphs of derivatives and we said to draw the derivative graph of cosine, remember we said the derivative graph of cosine was negative sine. And if I take the derivative of negative sine, I'm going to get negative cosine. Okay? So we need this information. We're also only talking about t equal to pi over 4 to pi seconds. And S of t represents a particle moving along the x-axis. And when I say a particle moving along the x-axis, and you say, Mr. Kukla, it's not moving along the x-axis, I say, yes, it's moving along the x-axis. So let's think about this. What's S of pi over 4? Well, that's cosine of pi over 4, which is root 2 over 2. And what's S of pi? Well, that's cosine of pi, which is negative 1. Okay? And what about S of pi over 2? That's cosine of pi over 2, which is 0. So if I think about this at time equal to pi over 4, my position along the x-axis is called root 2 over 2. I'm here. And then, at time equals pi over 2, we move a little further in time. Now we're going to have a value of 0. And then, at cosine of pi, at time equal to pi, our position is now going to be negative 1. So it appears as though this object is moving to the left the whole time. When we look at the graph of S of t from pi over 4 to pi, I see originally I have a position of root 2 over 2. At pi over 2, I have a position of 0, and at pi, I have a position of negative 1. These y values are my position locations on the x-axis. Okay? All right, now let's start asking some questions. This is S of t. I want to know when is the particle stopped. Well, stopped means velocity equals 0. So when does negative sine of t equal 0? Well, think about our sine graph. this is pi over 2. We're starting at pi over 4, and we're stopping at pi. So really, this is my whole graph. When is velocity? This is velocity, negative sine t. When is velocity equal to 0? Only at pi. At t equals pi, v equals 0. Okay. Next, what are velocity and acceleration when s equals 0? Okay, velocity and acceleration when s equals 0. First, I have to find when s equals 0. Well, conveniently, I have this nice graph here from pi over 4 to pi, and the only time that s equals 0 is at pi over 2. So that means at t equals pi over 2. That means I want to know v of pi over 2, which will be negative sine of pi over 2, which is negative 1, and a of pi over 2, which is negative cosine of pi over 2, which is 0. The object is not accelerating, and it's moving to the left. Okay, and in fact, we notice from pi over 4 to pi that the slopes here, not the y values, the slopes along this are all negative slopes. And that's why I know this particle is moving to the left, not just at pi over 2 moving to the left, because this is negative, but everywhere from pi over 4 to pi. This object, this particle, is going to be moving to the left. And remember that first horizontal line I drew, where at time equal to pi over 4, we had a location of root 2 over 2, and at pi over 2, we had a location of 0, and at pi, we had a location of negative 1. This object has been moving constantly to the left, and these negative slopes tell me the object is moving to the left. Okay? Next, what is the average velocity on pi over 4 to pi? Is average velocity v of pi minus v of pi over 4 over pi minus pi over 4? Or is it s of pi minus s of pi over 4 over pi minus pi over 4? Which one of these is average velocity? Well, remember, velocity's definition is a change in position with respect to time. A change in position with respect to time. This one is average velocity. So what would our average velocity be? Well, s of pi is negative 1. S of pi over 4 is root 2 over 2. And on the bottom, we've got 1 pi minus pi over 4 for 3 pi over 4. So can we tidy this up? Negative 2 minus root 2 over 2 times 4 over 3 pi. Cancel on the diagonal. And we get negative 4 minus 2 root 2 over 3 pi. This would be my average velocity. Well, if this is average velocity, what's this? What's a rate of change in velocity with respect to time? That's right, average acceleration. So I would do this if I wanted to know the average acceleration on pi over 4 to pi. Okie doke. All right, let's move on to the third question. I've only got 4 today. Third question. Got milk? In 1970, the average number of pounds each person drank per year was 273.8 pounds of milk per year. In 1980, that number was down to 245 pounds of milk per year. In 1990, we're down to 232.8 pounds of milk per year per person. In 2000, it was 209.9. You wonder why dairy farmers are upset? Look at all that consumption drop. And in 2012, we were down to 198.8. What accounts for this? Well, some of this is about the rise of soda, outdoing milk. Everyone used to drink milk at all their meals. Not soda, not juice, milk. We all drank milk, I promise you. But then soda started becoming really cheap and available, and a lot of people started drinking soda at meals. And then, around about here, we start having juices coming in, and we also have flavored waters, and now we also have the alternative to all of those things: soy milk, oat milk. We've got all kinds of non-dairy options now, almond milk. And so as a result, the dairy farmers have seen a tremendous continual drop in their demand for milk. So if you want to help a dairy farmer, go buy some ice cream, go buy some milk. They could use it. Okay, so I did an exponential regression on this, and yes, if you graph the points, it is exponential decay. And I came up with m of t equals 269.300 times 0.9924 to the t. Okay? And our input is pounds per our output is pounds per person, and our input is years. And by the way, this is t equals 0, t equals 10, so this is going to be t equals 42, right? So what I'm wondering is, what's m prime of 50 mean? I don't even really care what m prime of 50 is, I just care what it means. All right, well, let's take this calculator and type in our function. Our function here is 269.3 times 0.9924 raised to the x power. Okay? And if I go over to my table, I've already got this, remember, y equals set up with my first derivative and my second derivative. Okay? So we'll come over here to our table, and we want m prime of 50. As a number, I see that m prime, that's m of 50. M of 50 is 183.897, and we know those are pounds of milk per person. Still going down, folks. But if we come over here to the second derivative, the first derivative, m prime of 50, we get negative 1.403. Now, what are the units on this? Well, this is a rate of change in m. It's a change in m over a change in time. The units on m were pounds per person, pounds of milk per person per year. So what does that mean? Well, at time equal to 50, which is going to be 2020, when we get to 2020 next year, according to this data, the rate at which milk consumption is dropping, we know dropping because this rate is negative, this rate will be 1.403 pounds of milk per person per year. That means if in 2020 each person is expected to consume 183.897 pounds of milk per person, then we would expect that number to go down by 1.403 pounds to be 182.494. 182.494 pounds per person in 2021. Because the rate of change is we're reducing our consumption by 1.4 pounds per year. Now that's not constant, right? This is an exponential decay graph. So as time goes by, and yes, I'm sorry, there's no D value here, so this is headed towards zero milk consumption. At time equal to 50, the slope here is negative 1.403. So the rate of change at this point isn't going to be the same over here when we get to 60. It's less negative here. So Americans will be drinking less milk. The rate of change will be decreasing still, but not this much. So these big drop-offs initially, we're going to continue to drop off, but not infinitely. In fact, we're heading towards zero. It's very simple. Go hug a cat. Dairy cat. All right, last problem. Oh, is consumption increasing? I'm sorry. Is consumption decreasing? We know consumption is decreasing at a decreasing rate or an increasing rate? And I should be able to answer this question two different ways. The first way is graphically. We're decreasing, and are the rates decreasing or are the rates increasing? Are the slopes getting more negative or less negative? Okay, so what's happening here? Well, it appears as though here we have very steeply negative, then we have less negative, even less negative, heading towards a zero slope. Does that mean does that mean consumption is decreasing at a decreasing rate, or is consumption decreasing at an increasing rate? Well, I know the answer to this by looking at the graph, but it's going to be confusing for some people, which is why I want to go back to the calculator, and I want to look at m double prime. I want to look at m double prime of 50, okay? So let's bring out our m double prime here, and notice that m double prime of 50 is equal to 0.0107. This is positive. That means increasing rate. The second derivative is positive, and therefore we're decreasing, because m prime was less than 0, at an increasing rate, because m double prime is greater than 0. But Mr. Kukla, these values are heading down. Yes, m is decreasing. I agree. But what about the slopes? Well, if this slope is negative 4, and this slope is negative 3, and this slope is negative 2, and this slope is negative 1, look at these numbers. Negative 4, negative 3, negative 2, negative 1. We're moving this way. These slope numbers are increasing. So consumption is decreasing at an increasing rate. By the way, that's why the graph is concave up. Increasing rate. When the second derivative is positive, we know our graph is concave up. More on that during Chapter 5. Okay, last problem. Last problem is another position, velocity, and acceleration problem. S of t equals negative 16t squared plus 64t plus 80. This is Newton's falling object, or thrown object. We have an initial velocity of 64 feet per second. Our initial position, if we plug in a 0 for t's, we get 80. So we're originally 80 feet high. We're throwing this thing at 64 feet per second. There's gravity, or at least that kind of looks like gravity, but not really, because you expect negative 32. I'll explain that as time goes by. Okay, so first, what's s prime of 2? Well, we know the derivative of position with respect to time is called velocity, and so that's v of 2. So I need to take the derivative of position. I get negative 32t plus 64. And if I want v of 2, that's going to be negative 32 times 2 plus 64, which is 0. What's happening at time equal to 2? Velocity is 0. This thrown object is not moving. Why isn't this thrown object moving? Has it hit the ground? I don't know about that. When I think about this position function, object is going to go up and then come down. Now, when you look at this parabola, the slope on this graph is velocity. Well, I have a very negative velocity when this thing hits the ground. The thump, and the dirt goes flying. So, velocity equals 0 is when the slope on this position graph equals 0. Here, this is time equal to 2. Why is the object not moving at time equal to 2? It was going up, going up, going up, but gravity was fighting against, and slowly gravity wins, and the object hangs in space just for a nonce, and then gravity wins and pushes it back down to Earth. But right there at time equal to 2, this object is not moving. Kind of cool. Okay, next. What's s double prime of 2 mean, and what is it? Oh, this is 0 feet per second. Well, we know that s prime is v, and so therefore s double prime would be v prime, and v prime is a. So I'm looking for a of 2. Well, let's find a of t. A of t is the derivative of v of t. The derivative of negative 32t is negative 32. That's Newton's gravitational constant. Negative 32 feet per second is our force of gravity. Going down 32 feet per second every second. Okay, until we get to escape velocity. So, is there a place for me to plug a 2 in? No, because acceleration is constant. That force is acting on this object always down, 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 down. Why does the ball go up first? Because we threw it up. Up you go, ball, and then gravity, gravity, gravity brings it down. A of 2 is s double prime of 2, and in this problem, negative 32 feet per second. Okay? All right, last question. Let's see who is paying attention. Will you please find average velocity? If you know that s of t equals negative 16t squared plus 64t plus 80. Average velocity on 0 to 2 seconds. Okay? Hey, is average velocity going to be v of 2 plus v of 0 over 2? Is that average velocity? We had a velocity function, remember? It was negative 32t plus 64. So, can we find average velocity this way? Only if you want me to mark it wrong on your test. Don't do that. That is definitely not average velocity. Instead, to find average velocity, we need s of 2 minus s of 0 over 2 minus 0. So what's s of 2? Well, if I plug a 2 in here and a 2 in here, I'm going to have 4 times negative 16 or negative 64. If I plug a 2 in here, I'll have 128 plus 80. So if I combine like terms, I get 128 plus 16 is 144 minus s of 0. I plug a 0 in here, a 0 in here, and I get 80 over 2 minus 0. So that's going to be 64 over 2, or 32. Now what are the units? Well, the units here are feet, and the units here are seconds. So 32 feet per second is the average velocity from 0 to 2. Does that make sense? Well, let's look at the graph. Which graph? The graph of position, because average velocity shows up as the slope of the secant on that graph. Remember this graph we had of position from 0 to 2. Do we have a positive slope there? Sure do. The slope here, the average velocity, is 32 feet per second. Okay? That's not necessarily the velocity at a point. It's the velocity from here to here. It's our average velocity, the slope across that secant segment. All right, well, that's rate of change day 2, assignment number 42. Hope you enjoyed.